Yeah, today I'm going to tell you about some work that we're doing in the WASP group on upgrading alcohols. And we've been interested in this area for around about 15 years, but more recently it's been folded into an EPSRC Prosperity Partnership, which is in collaboration with University of Manchester, University of Texas, Johnson Matthey and BP. And so we're interested in alcohols mainly as potential sustainable alternatives for petrochemical fuels. So if we have a look here, we can have a look at just comparing gasoline to ethanol. So ethanol is a very widely used biofuel, but it's not actually a particularly good fuel. So you can see it's got, this one work? Well, it's got a lower energy density than gasoline, so it's about 70%. It's also got problems with water affinity, which makes it corrosive to current engine technologies. But the thing it's got going for it is renewable. If we compare it to a longer chain alcohol, something like N-butanol, we can see that butanol's got energy density that's much closer to petrol. And it's effectively water immiscible and has low corrosivity. So we can effectively use it as a drop-in replacement for petrol, and it can be used up to 100% in current engine technology. But unfortunately, it's not readily renewable. So when we first started this work, we kind of had this situation where we've got readily available bioethanol, which is a poor fuel compared to gasoline, and N-butanol, which is a better fuel. And the problem with butanol is it's usually made via the oxo process, so from petrochemical feedstock. It can be made via the ABE process, so from sustainable sources. This tends to suffer from poor conversion and selectivity, whereas bioethanol, on the other hand, we've known how to ferment for thousands of years readily from renewable resources. So we wondered if we could take a readily available bioethanol and use a catalyst to convert it to N-butanol to give us a potential route to sustainable biobutanol. And the reaction that we sort of stumbled across at the time was the Guerbet reaction. So for those of you that don't know what this is, you basically take a short chain alcohol and react it with itself to make a longer chain alcohol. This was discovered over 100 years ago, and it's generally considered to go via this particular mechanism. So you oxidize the alcohol, and then you have to use a basic co-catalyst, do an aldol condensation, and then rehydrogenate to the longer chain alcohol. And when we first started looking at this, we were inspired by this paper from the Ishii group, where they had discovered that if you took an iridium salt with a supporting phosphine ligand, so in this case they used bis-diphenylphosphenopropane and a hydrogen acceptor, then they could get moderate yields of N-butanol, so around about 20% in sort of relatively poor selectivity. So the selectivity is poor because you effectively get longer chain alcohols also in this process, which I'll talk about a little bit more later. So we entered the fray around about 15 years ago, and inspired by Ishii, we developed some catalysts based on ruthenium. And these were our first generation catalysts, so these cymene-ruthenium complexes supported by phosphines and phosphinoamines. And we could get similar yields to Ishii, but in much higher selectivity. Now, the biggest problem with these catalysts is that they're very fast, but they tend to decompose after, we run these reactions for about 4 hours, but in reality, they tend to decompose after about an hour and effectively die. So we developed some more stable catalysts. So by going to these bis-bidentate type systems, we found that we had to increase the reaction times, but we could now get yields a little bit higher, particularly in the case of this DPPM catalyst. So we could get yields of up to about 36%, but with a drop in selectivity. So since these initial reports, there's been a bit of an explosion in this area. So lots of systems that work for this now. So I've just picked a couple of literature examples. So the Baker-Jones system is very interesting. So they use a combination of iridium catalyst with a bulky transition metal base, and this gives almost perfect selectivity to N-butanol. The Milstein system, based on this acridine phosphine, is probably amongst the best available at the moment. So although the selectivity is quite low, it actually gives very high conversions of ethanol, and so it's around about 70% selective to sort of C4 to C10 alcohols. And more recently, people have started looking into non-precious metal catalysts. So the Liu and Jones groups basically came up with the same manganese catalyst around about the same time, which also works quite well. And if you're interested in this area, there are several reviews on homogeneous catalysis that I would direct you to. So this is all very good, but there are a few issues with Guerbet chemistry. So this is our standard reaction via acetaldehyde. And as I've already mentioned, our product alcohol can re-enter the cycle and give us longer chain alcohols, and this can just keep going round and round. So selectivity can be a problem. Probably more difficult is we have a competing Tishenko reaction where we form ethyl acetate and generate hydrogen, and then our water that we generate as a side product reacts with our alkoxide co-catalyst, and we get sulfonication of the ethyl acetate to form sodium acetate, which drops out of solution and effectively stops the catalyst working. So just to show you what this is like, in a typical post-reaction mixture, so using our fairly standard catalyst, you can see that we get this kind of gel of sodium acetate forming in the bottom of the vial. So we're still generating new catalysts, and recently we've developed this diphenyl phosphenol system, which is actually amongst the best catalysts available at the moment. So with this, we can get around about 41% butanol. So it behaves much more like the Milstein system, in which we get lower selectivity, but large amounts of higher alcohols as well. And the beauty of this particular catalyst is we don't see acetate dropping out of solution. So although we do still form acetate, it's actually held within the aqueous layer of the reaction. So just going to change topic a little bit here. So you'll have noticed a lot of our catalysts are based on bis bidentate systems. And early on, when we were first looking at this, we wondered if we could use a tetradentate PNNP system to improve the stability of these catalysts further. So we went away and made a series of PNNP catalysts, both imines and amines, and tested them under our standard conditions. And to be honest, we found that these were actually pretty poor catalysts. So we get low selectivity to butanol. And actually what most of them do is make ethyl acetate. But we were quite interested to see, we also got small but significant amounts of 2-butanol, which we were a bit intrigued about at the time. So, excuse me. Also around this time, Bella published this fairly famous Rumacho catalyst, which is an excellent catalyst for doing acceptorless dehydrogenative coupling of ethanol to ethyl acetate. So we wondered, these are all done in open vessels. If we did this in a sealed autoclave system like we do for the Guerbet reactions, would this also do Guerbet chemistry? And so we took Rumacho, also made some analogues where we varied the R groups on the phosphine and tested this under our conditions. And we did find that it actually does make 2-butanol. So again, we still mainly get ethyl acetate, but we now get higher proportions of 2-butanol too. So we did a little bit of system optimization with Rumacho. and basically found if we lower the temperature a little and increase the base a bit, we can actually improve the 2-butanol selectivity up to about 70%, which is very nice. So we're not entirely sure how this is formed, but we proposed a mechanism for it. So effectively, we can take our ethanol to acetaldehyde, and this can then go via Tishenko to give us our ethyl acetate, or Cannizzaro directly to acetic acid, and that effectively removes our base. Or we can form our aldol, which can then dehydrate to give us crotonaldehyde and onto 1-butanol. But we wondered if you could actually hydrogenate the aldol to give us 1,3-butane-diol, and this would provide us a route into 2-butanol. So we took our variety of catalysts. So catalyst 3 is a kind of exemplar 1-butanol catalyst. The other two are our catalysts that make 2-butanol, and we added portions of 1,3-butane-diol to see how this affected the reaction. And what we found is that we add the butane-diol to catalyst 3, it effectively keeps the same selectivity. So we mainly just see 1-butanol. But the other two catalysts do show an increase in the amount of 2-butanol. So this appears that there's a genuine ligand effect on the selectivity of the reaction. And we still don't really understand why these particular catalysts switch selectivity. So we're now looking at some computational work to try and work out where the variety comes in between these catalysts, and also why, when we change the R groups on the phosphine, we also move back to 1-butanol selectivity. Okay, have I got any time left? I'll very briefly talk about biodiesel. So this is an area that we've moved into more recently. So FAMEs are one of the first biodiesels adopted, and they're formed by taking triglycerides from natural oils, doing a transesterification to make a FAME. So FAMEs are quite widely used, but they do have some problems, particularly in cold climate performance. So if you look at a couple of properties, the cloud point and the pour point, the cloud point is the point at which crystals start to appear in the oil, and the pour point is where it ceases to flow as a liquid. And you can see that some of these are quite high, so you can't really use them in cold climate areas. However, if you add branching to these esters, so if you use the isopropyl ester instead, you can actually lower these temperatures to make them more useful. So long chain alcohols can also be used as a potential biodiesel source. So we wondered if it'd be possible to do a tandem hydrogenation Guerbet reaction. We could either take our triglyceride and hydrogenate to the alcohol, or transesterify to the FAME and then hydrogenate, and then add methanol and make a beta branched alcohol, which would hopefully have better low temperature performance. So we've done quite a lot of work on something related to this, where we take ethanol methanol mixtures to generate isobutanol. We published quite a lot in this area, and we have catalysts that work quite nicely. And so this works via a kind of double Guerbet cycle, if you like. And so the second half of the cycle would be like the methanation of the longer chain alcohol. So we took a couple of catalysts that we thought might do ester hydrogenation, and started with methyl propionate as a model compound. And we found that catalyst 10, Rumacho again, is actually very good for doing the hydrogenation, which is not that unsurprising. So we can get yields of propanol up to 96, 97%. We then just wanted to test it would do the propanol methanol Guerbet reaction, which we suspected it would, and it behaves pretty much as we thought. So we can get yields of isobutanol up to about 70% if we use high base loadings and longer reaction times. And then once we knew it would do both parts of the reaction, we tried to just put it all together and see if it would work. So we used a couple of methods. Method A was effectively just put everything in the same pot, increase the temperature so it was more likely to do Guerbet chemistry. Method B, we started with the first step where we do the hydrogenation at lower temperature, then we vent the system and then crank up the temperature to do the Guerbet part. And using these methods, we could get about 28% isobutanol with method A, but method B was clearly better. We can get about 40% isobutanol. Okay, so once we'd proved it would work with simple FAME equivalent, if you like, we went to the triglyceride. We started with tripropionine, and we do a sort of pre-hydrogenation step. So this is effectively the transesterification to make MEP, and then we do our steps 1, vent, and then step 2 to isobutanol in this case. And we found that we could get 46% isobutanol using tripropionine, which was very satisfying. We also found that if we did a mixed catalyst system, so we take catalyst 3, which is one of our best catalysts, we can actually bump this up to 63%, which is pretty decent. And finally, we've also tried it with some longer chain triglycerides, and we have found that these are also applicable to this chemistry. So I'm going to stop there. I think it shows that the Guerbet reaction is quite a versatile reaction for doing experiments with different alcohols for upgrading to more valuable fuels or fuel equivalents. So it just remains for me to thank various people. So Duncan for giving me a job, George and Jason, who were there for the start of this project all those years ago, and then Sam, Katie, Laurie, Josh and Ashley for doing some of the more recent work. I'd also like to thank Andres, Kush and Andy Logsdale, who are doing the computational work for us, and Benson for doing the crystal structure. And finally, got like the BP team and the JM team involved in the Prosperity Partnership. And thank you for listening.
Thank you very much. Do we have any quick questions?
Thanks, Richard. Enjoyable talk. Just wondered what you give me some sort of indication of what the total turnover numbers you're able to reach with those systems before you see, because you alluded to stability earlier in the talk, and the temperatures you're using quite high in some cases for this homogeneous catalyst. That's obviously a key feature. Yeah,
the turnovers for our systems are quite low, to be honest. It's usually around about 200 or so. We can improve that if we lower the catalyst loading, and we can get up to around about 1,000 turnovers. But that's pretty much the maximum we've found for our systems. There are much higher systems in terms of turnovers. So I know that the manganese system, they use that very, very low concentrations and run it for about a week, and they can get turnovers of, you know, sort of in the hundreds of thousands. But it's how real is that in a way? You know what I mean? So yeah, it's quite variable. But if you look in the literature, then they tend to be, most of the systems are sort of below 1,000.
Okay, so before I hand over to Charlotte for the closing remarks, I'd like to thank all the speakers of this session. So thank you.